There we go. Nobody say anything. Look at that. Nice big whiteboard. Okay, so equation for a ring. And by the way, just for the recording, we're doing number 30, chapter 22. Number 30. All right, so we've got a ring of charge. Z-axis, we know that E is equal to, now we didn't do the 4 pi epsilon naught thing, we did the K thing. So we said K, Q, Z over Z squared plus R squared to the 3/2 power down here. And that's a Z right there, not a 2. My 2's and my Z's start looking alike, and that's really irritating. I'm going to do my best to get that little line in there. All right, so question. Number 30 says, thin non-conducting rod. We put a positive charge Q on it. So we're going to go with capital Q rather than lowercase q. We can live with that. Radius R. Capital R. So how much E field do we have if Z equals 0?
0.
Yep. If you're sitting at the center of the ring, physically it makes sense that it's 0. Mathematically it makes sense that it's 0. What if Z is infinite? What kind of electric field are we looking at? 0. Because we're infinite distance away. I mean, it can't reach us. It's like, if you get far enough away, it looks like a point charge. You get far enough away from a point charge, and you don't notice it. So if it's 0 at infinity, and if it's 0 at the center, and it's non-zero in between, there must be a maximum somewhere. So the question of part C is, what Z gives us the maximum value? And then they throw some numbers in and said, what is that maximum magnitude? All right, so how do you find the maximum of a function? Take the derivative, set it equal to 0, find the max. Are you ready? Ready for some street calc? All right, here we go. So I'm going to say dE dZ is what I'm after. Now, I do hate the quotient rule with great hatred. So I'm going to take E and change it to KQ times Z times Z squared plus R squared to the negative 3/2 power. Just because I'm stubborn. And then I'm going to use the product rule on that stuff in the brackets. The stuff not in the brackets, it's not going to affect our answer at all. So you can either ignore it or just, write it off to the side and say, this is life. So KQ, we don't really care about. First times the derivative of the second. So first times the derivative of the second. Now the derivative of that guy, all right, I need chain rule, right? So I'm going to say negative 3/2 times Z squared plus R squared to the, okay, I got to lower that by 1, so it's negative 5/2 now, times the derivative of what's inside, which will be 2Z. There we go. So it is first times the derivative of the second plus the second times the derivative of the first. So the second is Z squared plus R squared to the negative 3/2. And what's the derivative of Z? 1. So that's it. And we're going to set this equal to 0. I ran out of room on the other side, so I'll put it over there. Set it equal to 0 and solve for Z. And then pray that's the maximum, not the minimum. I don't think it could be the minimum because we already found out it's 0 in the center and it's 0 when we're infinite away. So pretty good bet we're finding a maximum. All right, let's make it pretty. So Y, lose the 2. On top, we're going to have a negative 3z squared. On the bottom, we shall have z squared plus r squared to the 5 halves. Oh, yep, negative. Plus, we've got 1 over z squared plus r squared to the 3 halves. We're going to set the whole nasty thing equal to 0. Fine. Now, will that change my answer if I multiply this by KQ? No. All right. I'm not even gonna.
Shut up, Steve.
Thank you. I was gonna say it myself, but then I thought, Kellen, you're ready. Yeah, you serve a useful purpose in this class, more than one.
Oh, he's getting a pen.
Oh, he's getting something out. Does he have a weapon? Oh, okay. I'm recording this too, and I'm asking if Kellen has a weapon. That's probably not a good thing to end up on YouTube, right? Just for the record, Kellen does not have a weapon. His weapon is his sharp wit. And attitude. All right. So there's a couple ways to deal with this. I decided to find a common denominator. Because if I take this second fraction and multiply the top and bottom by z squared plus r squared, I'm going to have 5 halves on the bottom, and then I can go to town. So there's a couple ways to deal with this, but let's look at this. This is 3z squared plus z squared plus r squared all over z squared plus r squared to the 5 halves. Okay, I kind of did a couple things in one step. First thing I did is take that second fraction, multiply the top and bottom by z squared plus r squared. Now I have a common denominator, and I can join the two numerators together under a common denominator. So that's what's going on there. Let me be neat and put the little marks on my z's, so you know those are z's and not 2's. Now, Stephen, I don't care about the denominator now, right? Only care about the numerator. Let's set the numerator equal to 0 and have at it. So I'm going to claim here that when I add these together, I've got 2z squared, negative 2z squared, plus r squared equals 0. This is looking better and better, right? That means 2z squared equals r squared. If I square root both sides, let's divide both sides by 2 and then square root both sides. I've got z equals r over the square root of 2.
It's in terms of r.
Woo!
Oh, I'm thinking Steve.
It's okay, because big R we know, right?
Yeah.
Big R is a given. We're looking for z. Now their answer was like, I don't know, I don't remember what their answer was, but yes, you can write it in terms of R. So that's how you'd attack one of those. I think there's an example of one in the book where they deal with this 5 halves, 3 halves stuff, but it's still. So there really isn't a lot of physics there, is there? It's all the algebra that causes you pain and suffering. The functions get a little out of hand. All right. That was number 30. What was the other one? 36, yes, sir. Yeah, 36 had that goofy graph. Let's take a look at him. Are you all set on this one? Because I'm about to destroy it.
Where does the first equation come from?
This guy here?
Yeah.
That is what we derive for the E field for a ring.
Oh, okay.
You said we don't have to memorize that?
Not really,
So where would it be on the equation sheet?
because it's not on the equation sheet.
So we do have to memorize it.
Well, I would provide it if you really, really, really needed it. That's what I was kind of implying, was that since it's not on the equation sheet, would you have to memorize that? I don't know. It wouldn't hurt to memorize it, because for the big AP test, is it possible you would need it? And I suppose it's possible, though they don't really assume you have a bunch of random equations memorized when you take the test. They're more after your physics ability, physics knowledge. So, could they possibly have you derive the equation for E? That's a possibility. Though that would be one of those things where you'd hear the mourning of many, many, many physics students all at once in your mind. All right, I'm going to kill it. This is also on my notes on the Moodle page, so let's go. That was a big sigh. You okay? I can go back if you need to. Okay. Do you need a hug? Okay. I mean, Steven's available. All right. So, number 36, we've got a disc.
One of these days we're just kind of like a group hug.
Kellen will be absent that day.
Right after the AP test.
Yeah.
Right after the AP test.
Alan realizes that he failed. He's going to get a
No. All right. They give us a graph of E. And it's kind of a wacky looking thing. It kind of comes down like this. There's no asymptote, but what they're doing is they're telling us that this is like 8 centimeters. But notice what's happening at 4 centimeters. That's actually more exciting here because they have like E maximum up here, and they have half of E maximum here. Let me see. Yep, or they have 0.5 E maximum. I have E maximum over 2. Same thing. So the claim here is that there's some kind of EM happening at 8 centimeters when Z equals 8 centimeters. But when Z equals 4 centimeters, according to the graph, we're at half of E max. So that's kind of wacky. Okay, so then they say, what's the radius of the disk? Ha! All right. Now, we've got this cool equation for a disk. Again, I'm not sure I would spend your life memorizing this stuff, but we did not derive this, but the book does a nice derivation of this, and here it is. For a charged disk. All right. So, what's E maximum? When you look at that equation, how big can E get? Go for it, Anna. Sigma.
Yeah.
You're giving me the hand signs for sigma. Yes.
Yeah, because on the 1 minus, that can only get smaller when it gets bigger.
Yeah. So as Z gets bigger, so when we reach the point when this equals 1, then we've reached E max. And what we're going to do is we're going to stick 4 centimeters in for Z, and we're going to find out what value R is. So my thought here is that E maximum is going to equal sigma over 2 epsilon naught. And at 4 centimeters, we're at half of maximum. So, what would half maximum look like? That would be sigma over 4 epsilon naught, right? Equals sigma over 2 epsilon naught times 1 minus z over the square root of z squared plus r squared when z equals 0.040 meters. Okay, so let me explain myself. If maximum value of E is sigma over 2 epsilon naught, then half maximum is sigma over 4 epsilon naught. And the graph tells us it's at half maximum when z equals 4 centimeters, or z equals 0.040 meters. How you doing? Did that make any sense, Lucas? Okay. So there's our setup. What we're looking for now is R. And now it's just algebra. The first part, this part here, is interpretation of the graph. The rest is, okay, now I got to solve this baby for R, knowing that Z is a value of 0.040. So when you look at this, obviously you're going to go, wow. So I've got 1/2 equals 1 minus this nasty looking doohickey over here. All right, let's subtract 1 from both sides. I'll have a negative 1/2 here and have a negative fraction here. So I'm going to subtract 1 from both sides and multiply both sides by negative 1. So here we go. Let's see. I'm going to have, if we cross multiply this thing, I have 2z equals the square root of z squared plus r squared. So if I square both sides, I'm going to have 4z squared equals z squared plus r squared. So if I subtract a z squared from both sides, I get 3z squared equals r squared. So now if I square root both sides, I end up with z times the square root of 3 equals r. And that's the answer. It's z times the square root of 3. So 0.040 times the square root of 3 gives me r. So one of them was like, take r, divide by the square root of 2. And this one was like, take z and multiply by the square root of 3. There's just these weird little nice answers come out if you play with the algebra. Okay, obviously on the test, I can't give you one that takes 19 minutes to do. Because there's 3 problems, and it's the basics of, okay, what's an electric field? How do you find things? How do you find the force between 2 particles? How do you find the force between 10 particles? But I think it's a good idea to give you another night to pound down this. Okay, so those were the 2 big ones. Those were the 2 that people had the most worry about. Are there any others that I can help you on the assignment before we attack the review?
You can do number 43.
43, you were going to say that too?
Say like C.
All right, let's take a look at it. All right, so number 43, Doc. Oh, okay, hang on. So this is different than I thought it was. Hang on. I must have been thinking about 48. 43 says, a charged cloud system produces an electric field in the air near the Earth's surface. A particle of charge, negative 2 times 10 to the negative 9 coulombs, is acted on by a downward electrostatic force of 3 times 10 to the minus 6 newtons when placed in the field. What is the magnitude of the electric field? What's the magnitude and direction of the electrostatic force on the proton placed in the field. And then what's the magnitude of the gravitational force on the proton? And then what's the ratio of the electric force to the gravitational force? Ooh, whoa. Let's give that a shot. Okay, so let me, are you folks okay erasing this? Anyone still cogitating, writing, taking good notes, saying, wow, algebra is crazy? Okay, so we've got this cloud of electrons, this charged cloud system, but let's not worry about the details of that. What we're mainly concerned with is that there is a particle in it that has a negative charge, and it's experiencing a downward electrostatic force. So this negatively charged object experiences a force this way, and it is 3 times 10 to the minus 6. And he has a charge of negative 2 times 10 to the negative 9. So electric field strength, remember, is force per unit charge. So if they say, what's the magnitude of the electric field? We'd say just that. 3.0 times 10 to the 6 newtons is felt by 2.0 times 10 to the minus 9. This will give us the magnitude. Notice I did leave off the negative sign just because I want the magnitude.
Left off the negative sign on this one too.
I did. Thank you. You caught me. Thank you. Kept me from falling. All right. So 3 divided by 2 is like 1.5. So minus 6 minus a negative 9. That's like to the third power, yes? Okay. Question. What's the direction of this field? Up. But this little particle is feeling a force down. What are you talking about, Steve?
It's positive. Field is positive.
Okay. So remember, we decide the direction of the field based on what would happen to a positive charge placed in the field. So if the little baby positive charge, Ralph, were placed in this field, this negative charge feels a force down. That means a positive charge would feel a force up. So remember, negative charges always swim against the current. When you look at the picture, you'd say, all right, let me get some different color here. There we go. Look, this field is this way. Why? Because if I placed a positive charge in this field, it would experience an up force. You place a negative charge in this field, that blue field I just drew, it would experience a down force. So he's right. It would be an up answer. So that takes care of A and B. Or we'd say positive J hat, right? That's probably what they did. All right. Okay. What are the magnitude and direction of the electrostatic force on the proton placed in the field? Okay, we got the direction because the proton's a positive charge. It's going to feel up. The force felt by a proton, we'd say F equals E times Q. And of course, it's 1.5 times 10 to the third newtons per coulomb. And a proton is 1.602 times 10 to the negative 19. So whammo, that's easy to get. Just have to have a good calculator with charged batteries. And I'm getting like 2.4 times 10 to the minus 16 or something like that. Okay. Could that be the right answer? All right. Next. It gets bumpy from here. What's the magnitude of the gravitational force on the proton? All right, set a proton in here. We'd say, oh, he's experiencing an electric force up, a gravitational force down, which is just mg. So we need a proton mass. This is where Jake would Google because he doesn't like using our appendices. But if you're old school, you just turn to the appendices and it says proton mass is 1.67 times 10 to the negative 27. So we can come up with the weight of a proton without too much trouble. Make sure I got this right. Yes. So this is one of those big constants of the universe. As far as we know, rest mass of a proton. 1.67 times 10 to the negative 27 times 9.8 gives us a really tiny answer. 1.64. Probably too many sig figs, but let's go with it. Negative 26 kilograms. No, what an idiot. Newtons. Some days. All right. Then they want the ratio, right? So what's the ratio of the electric force to the gravitational force? All right, check it out. The electrical force is 10 to the minus 16. The electrical force is 10 to the minus 26. It's 10 orders of magnitude smaller than the electric force. So, yeah. So the ratio of electric to gravitational, they're using EL. Just go for it. 2.4 times 10 to the minus 16 on top. And this 1.64 times 10 to the negative 26 on the bottom. So the answer is wowzers. Right? 2.4 times 10 to the minus 16 divided by previous answer. Might be a little bit off due to rounding or whatever, but I'm getting like 1.5 times 10 to the 10. Okay, no units on it because it's a ratio. So that's like 15 billion times stronger. So in a lot of cases when we do these problems, we don't worry about gravity. We say, we got a proton between two plates. What's its motion in the x and y axis? Do we factor in gravity? Not so much. Because in general, the electrical forces are billions of times stronger. So it doesn't even tickle the sig figs at all. It's like, tweak. Yeah, no difference. Are you okay, Amanda? You're just really tired? Okay. All right. All right. Anything else I can help you on this assignment before we attack the review? Okay. We can do some whiteboarding. But last hour they also had a couple of questions on the multiple choices. Anything I can help you with?
Number 5.
Yes, sir. Number 5 says, a small object has charge big Q. Charge little q is removed from it and placed on a second small object. The two objects are placed 1 meter apart. For the force that each object exerts on the other to be a maximum, q should be... we actually did this with masses. I don't know if you remember this, but there was like this big mass, and we take a little bit of mass off and we move it away. And we said something like, what should the ratio of the masses be in order for the force, the gravitational force, to be the largest? And it was half and half. We cut it right in half and do it. So I'm guessing it's half, but we can prove it. Am I right? Number 5 is C. Yep, it is. Exactly half. Okay, let's see if we can I don't know if I can prove it, but I think I can. All right, I need to kill off all this stuff, though. All right, so we've got this charge, Q, charged object Q. Okay, next thing you know, we take a piece of it and we move it over here, some distance away. So now I've got Q minus little q and little q here. And the force between them is going to be K, Q minus little q times Q all over R squared. And I'd like to maximize that. I'd like to know what is the biggest, what would little q be? Let me see this. Yeah, I want to maximize the force and figure out what little q should be. R is a constant. We're just going to pull them apart a certain distance. K is a constant. So if I want to maximize this, I'm going to take the derivative of this with respect to what? Q, little q, yeah. And then set it equal to 0. Now, like I said, I can take the derivative of this with respect to q, but K and R squared are just going to sit out this game. They're not going to do a thing. And over here, I'm going to have big Q times Q minus Q squared. And I apologize, this is the original function. I'm not taking the derivative yet, heavily. So now I'm taking the derivative. df dq is equal to, all right, again, constants. If you want to write them down, that's fine. They're not going to do anything. The derivative with respect to little q is going to be big Q minus 2q equals 0. Well, if q minus 2q equals 0, that means q equals 2 times little q. Ah, we win. That means we cut big Q exactly in half. All right. But we actually did that problem with mass one time, a long time ago in a galaxy. Well, this galaxy. Anything else? Ma'am?
Can you explain 11 again, Paul?
Yes. Number 11 is a little freaky. Let's look at it. I've got a T on its side. This is negative big Q. This is positive big Q. And we've got some point over here. And we want to know the direction of the electric field right there. Okay, the only way to figure it out is to get Ralph again, your little positive test charge, and place him right here. So I've got little positive test chargey. What is he going to do to the positive test chargey? Attract or repel? Attract. So he feels a force exactly that way. What's this little guy going to do to Ralph? Repel. So he feels a force directly that way. Now, despite my drawing, are those two forces going to be the same or different? The same. And they're going to be at the same angle, though opposite. So here's what I'm thinking. If we add these two forces up, if I break this guy down into components, and I break this guy down into components, what's going to happen to these two sideways components? And what's going to happen to these two up components? So the direction of the field is up. Isn't that? So step by step. Don't try to, if you try to solve the whole problem at once, migraine headache. But just imagine putting a positive test charge there and say, okay, what does he do to him? What does he do to him? You can work it out. You can logic it out. And what was 12 the other one?
Yeah.
Okay. An electron traveling north enters a region where the electric field is uniform and points west. All right. Let's figure out these compass headings here. North, south, east, west. It's telling us that the field is uniform and points west. La 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 la. Okay, that means if I put Ralph in this field, he's positive and he's going to feel a force toward the west. If I take an electron and stick it in this field, which way will he feel a force? East. So, electron, there he is. He's feeling a force that way. Now, he's traveling north. So he's shooting this way toward the north. What's he going to do? Yeah, he's going to feel an acceleration toward the east. He's going to do this projectile, sideways projectile motion to the east. So his path is going to kind of look like, he's going to, if he starts going north, he's going to go, ah, and more of his velocity will be toward the east. So C, veers east, is the answer. They're going to try to trick you with that, right? The field points to the left, but negative charges placed in the field will feel force to the right. Negative charges always swim upstream. They're always going to want to go the opposite way, which makes sense, but it's easy to get confused. Okay, we're coming down to, let's see, second hour goes to 49, so we're coming down to about 12, 13 minutes or so. Anything else I can help you on the review? Got through the multiple choices? Did you get through the problemsies? Not quite yet? All right, so it's whiteboard time. Let's take a look. Unfortunately, there are 8 of them here, or 9 of them here, so let's try, let me pull one out here that's a good one for you to whiteboard. I think I'm going to pause my video here so that